Everyone. Thanks for coming to my talk, despite there being a more interesting talk next door or upstairs. I hope I don't disappoint you too much. So about myself, I introduced myself yesterday talk. So if you were there, you know me, and probably you know me already. Just gonna say my name is Zeeshan, and I live in Berlin. A bit of a recap on Zbus, if you don't know. Yeah, someone asked already. Well, Zbus is a pure Rust dbus library, basically. And I'm one of the main people who made that happen. And what is Varlink? Does anyone here don't know what Varlink is? It's okay. It's not a crime if you don't know. Okay. Anyway, so I'll go faster on this one. Well, it's basically a IPC mechanism, just like dbus, and it's now being pushed by systemd as the replacement for dbus, more or less. Yeah, it's quite interesting, and it's basically just JSON. Like on a basic level, it's JSON payloads on Unix sockets. That's what basically it is. And I was very suspicious of this, right? Like I was always brought up to believe that dbus is very efficient binary protocol, and protocols needs to be extremely efficient and all that. And then when Lennart says like, yeah, we need to do something with JSON, I'm like, what the hell are you talking about? So I had many debates with Lennart about this, quite a lot. And he kept on telling me that like, I kept on asking like, okay, parsing cost, like JSON parsing is sort of expensive, and that matters. And it does matter. But his argument was that what matters a lot more is context switching. And when your CPUs, modern CPUs, are designed for parsing data, for processing, basically. But they're not really designed for dealing with context switching all that well. Yeah, they have been, but they don't do it so well. So that was his argument. And I was like, which one is more important here? I was sure that it's me who is right and he's wrong. And also it's like peer-to-peer, right? So it's with dbus you have a daemon usually sitting. You can do peer-to-peer with dbus, of course, but that's not the default way of doing things. And if you want to do P2P, you might need to do some of the work that the dbus daemon does for you. People don't usually do that. They do, but not as much. And it's so I was in the denial phase, right? Like I was like, no, he's wrong, and I thought I can show him like I'm right and he's wrong. So I did as what any good engineer would do in my position. I benchmarked things to prove that I'm right and he's wrong. So I wrote these benchmarks. You can find them actually on GitHub, on my GitHub space. And I wanted to compare various binary formats against JSON, both in terms of time, like serializing, deserializing, and also space, like how much, what's the size, encoded size. And I've found like compared to dbus, JSON was not that bad actually, and I was not really proving my point that well with these numbers at least. And especially here, like I have highlighted these specific numbers because I think these are the most important ones. So when you do dbus, usually your messages are sort of small or medium size. They are not too big usually. They're typically at least, hash maps and actually dictionary in dbus terms is quite widely used in the dbus world. So you use hash maps quite a lot. So it matters. If your data is hash map based, then that's a very fair comparison between dbus and JSON if you want to move more towards a JSON based protocol. So these are the numbers that are most important, and they are not that off, right? Like it's not like it's 4 or 5 times or something like that. So these are the encoding decoding speeds, right? Like but what about size, you might ask? Also similarly, like it's not that big a deal in JSON versus Dbus. If you have like vector-based, by which I mean like if you have structs rather than dictionaries, where your keys are not like named right in the encoding, so then Dbus starts to win really well, but still not like gigantic numbers, right? That gigantic difference between the numbers. So I thought perhaps that's not a bad idea. So I started looking into like what are the maybe there are some other advantages too of Varlink. So first of all, the best advantage of it is super simple, and that's always good to have something simple. And your IPC becomes your logging, right? Like whatever you're putting on the socket, you also put on your log directly. Your method calls, your method returns, all of that, and you have the log already. You don't need to format a separate log for all your communication. So that's actually a pretty cool thing. Coming from a Dbus developer background, to me that's a big advantage. Pipelining is also a big thing in the Dbus world. People assume that, but it's not fully guaranteed like that you can do pipelining. So there is no guarantee in the specification that the method calls that are arriving at a service, they have to be processed sequentially. And even if there was such a requirement, it would be very hard to implement it in Zbus and stuff. So for various reasons I won't go into. But pipelining is not so easy there. But in case of Varlink, that's guaranteed by the spec that if the methods are processed in the order they are received on the service. So you can do pipelining, which means basically that let's say you need to make 10 method calls, right? So if you do one at a time, you will have to send a method call, then wait for the reply, then again and again, and that's a lot of context switching. But if you put all your method calls, serialize them, send them over a socket all at once, all 10 of them, that's reducing a lot of your context switching. And systemd folks and Dbus broker folks, actually, they did a lot of measurement, benchmarking, and they found out that pipelining, for example, their handshake in Dbus helps with latency quite a lot, like very significantly. So, for performance reasons, for reducing latencies, this is extremely important. And then there are specific advantages, like JSON is a very ubiquitous, I never know how to pronounce it, ubiquitous format in the Rust world. Like it's used extremely a lot, like that's so much. And there is a crate, Serde JSON, which was the first Serde crate actually, and it's super good. It's well tested. It's used a lot, so we can really rely on it. And that one. And you have nullable types, which does not exist in Dbus. I was saying yesterday, Allison solved that problem with gvariant, but gvariant never became Dbus, so we never had nullable types, which is something that is used quite a lot in the Rust world with the type called option. Anything that is optional, you just put it in this enum, and then it becomes optional. So we can do that now without any problem. Connection sharing, in Dbus world, it's designed so that you have one connection per process, and you share that with all your threads, with all your tasks, and all the code. It's designed around that. I'm not saying that you cannot have multiple connections in a process. You can have it, but there's also a limit by the broker, especially in the system with the system Dbus. You have quite a low limit per user. You can have how many connections you can have at a time. So because of that, most application and services Dbus prefer to have one connection and share it around. And that means a lot of problems for at least for Rust applications. I'm guessing for others too. And to show you what kind of problems, like let's look at the receive pipeline in Zbus, how we receive messages, dbus messages, and process them. So we have something called a socket reader with each connection, and that socket reader basically reads from the socket bytes, and then it sends the same message to all the tasks that need that message. So it does actually a bit smarter than what I'm showing here. It's not like it's sending to all the tasks, all the messages. No, it's based on match rules. So each task or thread have a match rule that it receives messages for that rule. So it's not so wasteful like this, but it could be like in a specific scenario. So you can have multiple copies of the same message, and that's bad. But we have a solution for that in Rust world. We have a type called arc, which is atomic reference, basically. So you can put something in an arc, and then you don't need to deep copy anything. You just clone it each time, and the reference keeps increasing, and you can have multiple owners of the same message. So that solves the problem. So we read the bytes, we put it in a message, we put it arc around it, and we can then broadcast to whoever needs it. No deep copying or anything. So that's much better. But there's still some problems, right? Like there is still like 2 copies being happening. Even if there is just one task, one consumer for messages, it's still like the architecture is so that there will be a socket reader task, and that will copy twice the message bytes. And then you have atomics. Atomics are like nowadays, in high-end machines especially, they're like not a problem. But they do have a cost. So it depends on your use case, where you're running things, and a lot of things. But atomics do have a cost. So they're not completely free. And also interior mutability is something we need, because if we have one connection and it's being shared, and if anything is mutated in the state of the connection, we need some mutexes, basically. And mutexes can have like deadlocks and all the other problems that compiler cannot really help you with. So it's not ideal, and also they have a cost. Like if there's a contention, so then no 2 tasks can at the same time, or 2 threads can access the state at the same time, right? So that's not ideal either. And then you have like multiple tasks. Like even in a simple case, you have at least 2 tasks or threads, and it adds to the latencies of scheduling, right? Like scheduling is always bad. So what can we do in Varlink that is better? First of all, Varlink is P2P, like peer-to-peer, and it doesn't have any handshake like Zbus does. So creating connections in Varlink world is super cheap. It's not a problem. You can have as many connections as you want. There is no limit or anything. If a service puts a limit to connection, that's another thing. But at least by typically, it's not there. And if you have cheap connections, that means you can basically have unlimited connections, theoretically at least. And that's really cool, because then we can have something like this, that each, you can have one connection per task or per thread, and each task can then directly read from its own socket, like because it has its own socket. And then it can read into a buffer, and then you can deserialize directly in that task from that buffer, also with 0 copy. That's why in here I use a lifetime. I'm not sure if everyone here is comfortable with lifetimes in Rust, but we will be seeing them here. So in here, like there's a 0 copy string deserialization here happening. So you can have something like this, and that means you get rid of atomics completely. You have only 1 copy of messages. You have exterior mutability, which means that you don't have any possibilities of deadlocks. You don't need mutexes. You don't have the cost of mutexes. The compiler at compile time will ensure that no 2 tasks or no 2 contexts are modifying or have this mutable reference to the same connection or whichever state you need to mutate. So it's all happening at compile time. No mutex is needed. And also, you got rid of the task, so you don't have to have a separate task for reading from socket to send to all the interested parties. Every interested party can do it directly themselves. And also, I noticed that we can actually do something called NoSTD in Rust world, which means like standard library of Rust. There's API that assumes an operating system, like, for example, sockets, right? Like, you can't just create sockets out of thin air. You need your operating system for that. So when you don't have an operating system or unsupported operating system and you want to code for that, then you can do something called NoSTD. And we could do that, at least in the core of the library. So and also, we can do something called no alloc, which means that you don't do any allocation whatsoever. And so if we could do make this possible, then it would be also interesting for developing firmwares and microcontroller code, like bare metal microcontrollers especially. But why did I think of that? Why did I think of no-alloc and no-std? So I'll take you back some months when I was working at a company, which now is no more, unfortunately. But we were doing electric vehicle charging stations, and in there we had microcontrollers that were responsible for specific tasks. And the biggest one was the charging controller that was responsible to talk to the car and all that. So and we had these firmware developed in Rust in there, and that were talking over USB to the Linux board, which was the brain of the whole system, and that could talk to the internet and all that. And on the Linux board, we have different services like running apps, basically, and we needed some kind of abstraction. So we used Zbus, and we had something called, we called the gateways. So for each charging station, for each microcontroller, we had a gateway that was exposing a Zbus API to the higher level API or Zbus for the services. And then, yeah, so this was this kind of architecture. So I just thought, like, what about we cut the middleman, right, in here? So if we remove the gateway, and I'm not even talking about the Zbus daemon, because there's also Zbus daemon between, so there's multiple middlemen, middle persons. So yeah, we will remove both of them, and we can just directly expose a high-level API from the microcontroller. That would be so cool. But Zbus is doing no-alloc in Zbus is almost impossible for various reasons, some of which I mentioned already. So it would be really cool if we had such an API with no-alloc, and we can use that instead. So I started looking into all those things. I was like, okay, now I'm in acceptance phase. Like I think it can work. So maybe there's already a Rust crate, and there was. Can you guess the name? It's called Varlink, so it's basically just the same name. However, I noticed immediately there are some issues with it. First of all, it's blocking API. If you're doing IPC, excuse me, and you're mostly waiting on sockets, right? So it's a place where you're more I/O bound than CPU bound, and this is where async API would be really cool. And also in async in Rust world, at least for the application development, it's super awesome. People demand that. So when I wrote the first Zbus API, it was blocking, and the first issue was about, one of the first issues was about, thank you, about blocking API. So yeah, async is important. It's also designed for code generation, so it's not that it supports code generation, but it's designed around it. So that's the default way of using it, advertised way. And it's unmaintained. Became somehow one of the maintainers, but I have not much idea about the code base and everything, so I'm not doing any maintenance. So I was like, we can do better. Let's start from scratch. Since I wrote Zbus, maybe I should also write the Varlink, the replacement for Zbus. So I created something called Zlink, and I first named it something else, but it wasn't so nice, so I renamed it to Zlink. Anyway, it's first of all, the first goal would be it's async primarily. Also, no STD and no alloc support. Code generation supported but not required. That would be the goal, so that it's not like the only way to use it nicely. And also to take as many lessons as I could, because I worked on Zbus, multiple iterations of it over the years. Now it's Zbus 5, so we had many huge changes in between. So all those years of experience, I try to use it. And also chaining and pipelining, as I mentioned, it's super nice, so that would be nice to have. So this was the architecture I decided on. Basically, the cyan-colored ones are the ones that you will use directly. All the others you will not use directly, because Zlink provides all of the APIs underneath that you need to use. Re-exports a lot of it. Like, for example, the Tokyo, Zlink Tokyo, it just re-exports the whole crate API if you enable the Tokyo cargo feature. So it depends on the cargo feature, which features you enable in Zlink, and it enables that backend for you, basically. And the core is just like the very core of it, very abstract, very not non-specific, no STD, no alloc in there, no allocations at all. Yeah, so it provides also these abstractions for transport that other crates on the higher level can implement, like Zlink Tokyo can do that. And also this May heap is an abstraction library I wrote for collections that makes it possible for you, based on your cargo feature that you enable. So it either uses allocation or it does not use allocation, but rather stack-based collections. So it's a collections API, basically. So I was like, okay, is it a match made in heaven? While I was working on, when I started working on that, and I realized that yeah and no, like yes, because of all the reasons that I mentioned before, but also no, because it's, first of all, it's like designed by C developers. Like, I'm sorry to say, but no offense, that it is like it shows in some certain cases. For example, there's no size header, right? Like, it's just JSON strings null terminated. And null termination is something that is taken for granted in C world, but in other programming languages, it's not a thing. So for example, in Rust, we don't have that usually. It's if you have that, then it's called a CSTR type. So that makes a bit difficult, because you need to then find, if you have pipelining involved. If there was no pipelining involved, then yeah, sure. At the end of each message, you get a null byte, right? So it's easy. But without that, you need to find the null byte to figure out where the message ends, or parse the JSON in a streaming way, which is not possible with Serde JSON. So it's a bit of a pain. But I did what I could to make it as fast as possible, and I use a library called memchr, which uses SIMD and all kinds of tricks to make it as fast as possible to find specific bytes in a buffer. So that helps a lot, actually. And encoding of the also the Varlink, it encourages allocations and also reparsing. So if you have like this, your method call, then it's easy, because your method comes first, and if you can assume this order, then it's simple, because you can first read the method, and then you can deal with it, like the parameters, in an appropriate way. But if the method name comes later, you don't know how to deal with it, because whose parameters are these? So you have to first put the parameters somewhere, and then check for the method and stuff like that. There's other reasons too, where because of which it's sort of pushing for allocations, or reparsing at least. But like this sort of I solved with assuming field order, which I think it's okay, but I'm not too sure about it. But we can talk about it later a bit, if I still have time, a minute or so. And there were some other problems too. I had, like, for example, no alloc wasn't as easy as I thought. It was actually quite hard to do. But I did manage to do it in the core. It's no alloc. And there was a lot of bugs that I found out in the crates that I was using, libraries that I was using. For example, bugs in Serde. Okay, thank you. And also one bug, a very weird but corner case Rust bug that very few people encounter ever, and I was so lucky that I also encountered that. But there's a solution now. It's in unstable, I think, Rust, but hopefully it will be in stable soon. But yeah, there were some other bugs too. So what is the status? I have a low-level API in Zlink, which works. I won't show that to you. I don't want to scare the hell out of you. We also have high-level client API, which is the more important bit because there's already services, but the clients are waiting for some nice Rust interface. So I can show you the code very quickly. Basically, it's very similar to how you do it in Zbus. You have something called a proxy. A proxy represents a remote interface in Varlink. You give it the name of the interface, and then you just define the methods that you have, and the return type and the error type. Yeah, and it's I'm using lifetimes here just to demonstrate that it can be completely zero copy deserialization and serialization. And the way you use it, that was a declaration. The way you use it, you just directly create a socket, and then it's like a connection, and then you can directly call methods on that connection, because the previous example where we saw this let's say calculator trait, so that trait is then implemented automatically for connection. So when you have a connection, you have that trait implemented already. So you can just directly call methods on the connection itself. This is very different from Zbus, where it's a bit more complicated. You have to create a proxy and all that with a connection. But here you can just deal directly with connection itself. We can also support pipelining. The macro generates for you the chain methods so that you can chain your method calls, and also a trait that goes along with it that enables doing something like this. It's the same example as before, but this time we are chaining it. So you send all the method calls at once. They're serialized, and then when you say .send, they are sent. And once it's sent, then you can get a reply handle, and then you iterate. It's a stream, basically. In the Rust world, we call it stream. Or async iterator, you iterate over the results, basically. There are some other goodies. You can do multiple replies. It's very easy, actually, to do. I don't have an example here, but yeah. And also, we have a really nice, I think it's nice, introspection API as well. We also have a pretty good example of that in our repo, so if you want to check it out. There's low-level, well, more like mid-level server API. A bit of warning before I show you, it's not for the faint of heart. It's like if you want to implement a service called calculator, you do it like this, and you handle very, on a low level, you declare your types, basically. What are your method call type, and usually an enum, but you can do whatever you want, actually, in here. This is very liberal, but very low level. So I know it's scary, but I'm hoping to work on the high level server API this month. Hopefully I'll be done soon. Then you can use that one and not even look at the low level one, rather low level one. Bare metal embedded is, I'm a bit reconsidering that for multiple reasons. One of them is that I didn't think about the fact that in this scenario, for example, if you don't have the gateway, if you remove the gateway and you have like more direct connection with the microcontroller, you will need a USB device, and how can two processes talk to the same USB device at the same time? So you need some sort of gateway still in this architecture. So that's one of the reasons. The other one is like a lot of these systems, in this case it wasn't the requirement, but in a lot of these safety critical systems, the requirement of latency is extremely low, and JSON cannot possibly provide that. You have to use an extremely efficient binary protocol. Not Dbus. Please don't do that. That's not low latency enough. And yeah, and noalloc complicates things. But we still will avoid, even if I remove noalloc, we will still avoid allocations as much as we could possibly can, and we would. And atomics will still be avoided completely. Still no interior mutability. Yeah. And I might also think about custom JSON deserializer, because of one of the I mean, one of the reasons is like the null byte detection that won't be needed anymore, for example. So when I'm parsing myself, I know that there's a null byte expected. A generic JSON deserializer doesn't care about that because that's not something that happens in there. So that would be one of the reasons. But there are other reasons to also consider this at least. Don't want to do that, but might need to. And just before I finish, reminder that Zbus is not going away anytime soon. Maybe it will be, but not like tomorrow or next year. It will remain as legacy for a while. So yeah, that's it. Thank you.
And now we have time for questions. If there's anyone who thinks they should still use Zbus.
Alison had a question, no?
Actually, you probably don't know what I'm talking about because you've probably already forgotten about Zbus. So like the, yeah, I don't actually remember either what it is. But
so no questions? I'm really surprised. Like, oh, there is one.
Earlier, you had in your code gen for the client API, it was a trait for your the proxy object, right? And you said it implemented this trait automatically for connection. That's just for the generic connection. So
yeah.
all the traits are implemented on that connection, and you just have to be careful with what you're importing into your context.
Basically, yeah.
Okay. Yeah.
So as easy as it can get, right?
Okay. Yeah, that makes sense. Thank you.
Don't be shy. I know I didn't explain everything well.
Okay, here you go.
Hey, first off, thank you very much. I tried converting something I had with Varlink crate to this one, and it indeed looks much better. And I'm definitely waiting for the higher level API and the code gen improvements, because when I did it the first time, I made a typo in an argument somewhere, and so everything wasn't working just because I had a typo in one of the functions. And I think that's, the high level API will likely greatly help with that. So thank you very much.
No. So there was no question? Okay. That's okay, thank you.
Yeah, as far as I know, in JSON there's only ints and floats. So Rust has this multitude of very strictly length, like uint64t, whatever.
Yeah.
I'm not even sure how the signs are defined in JSON. So how does that map?
So for non-generated code, it's up to you. So you can use any of those integers, and it will just be a number, generic number in JSON, right? At least there is a separation between integer and floats. So if you don't use float, you have integer, then you don't have the decimal part, right? Fractions. But otherwise, yeah, it's like that. But one problem with the code, problem is for code gen, because in code gen, it just sees that it's a number, generic number, and what do I translate it to? But Varlink interface files, the introspection, that code gen uses, at least it differentiates between float and integers, right? So so at least there's that. So we can do some of it automatically, but a lot more. If you need more fine-grained stuff, then you might need annotations in the code gen for that. If you're defining the trait yourself, then yeah, you choose the Rust type, and it just translates automatically to whatever is the appropriate type in JSON. Not a problem.
Thanks for the talk. It was really quite insightful, actually. Interested to actually try it out myself. Do you have any thoughts on rate limiting, the topic in general? Do you have anything implemented for that? Because I could imagine that having, unlimited connections could be a denial of service problem.
It could be, yeah. And yeah, that's a good question, because I have thought about, not specifically for this, but in general, there's a lot of like security-related things that Dbus broker does for you. So some of them would make sense to have in a library like Zlink. So yeah, I need to look into that down the line, like some of these very essential features for security. But I'm hopeful that people will also file bugs about it, so then I can look into it.
This might just be my misunderstanding, but I'm just curious. When you say connection, is that the same as just a message, or is this actually a connection-oriented protocol where there's an established relationship between the client and server?
No, it's an actual connection,
okay.
Like basically Unix socket connection. Yeah.
Yeah, as far as I know, Varlink doesn't mandate that it's Unix socket, right? You
It
can
does
talk
not,
over
no.
standard in out, you can pipe it over SSH, etc.
Yeah.
And so I guess there's also ways to connect to these other ways. So.
Yeah, most definitely, and I'm hoping that people will add
because
those.
that's really the cool thing about Varlink, that it doesn't prescribe this kind of what's the substrate that you run this on, right?
Right.
I think I know the answer today, but I want to know like the answer in a few months from now. If I define a trait and one of the types that I put in that trait is owned FD, what is going to happen?
Sorry, types like owned FD in where?
Like if I create the trait and I make a method that wants to take an owned FD.
Yeah, I'm looking into that to support file descriptor processing, because that's not simple, because you cannot just pass file descriptor as a data. You need to send it over the socket in out of band way. We solved it in Zbus more easily, because in Zbus we have our own serializer, deserializer, so we had some special support in there. But if I continue using the JSON, set the JSON, then it won't be same. But also there's a difference between Dbus, is that in Dbus you have a specific type for file descriptor. I think, as far as I remember, Varlink doesn't. It's just an integer. Yeah.
Yeah, systemd already has a couple of interfaces where they do the same thing that Dbus does. They say, okay, I put a 0 here, and I understand that that's an index into the.
Yeah, but there's no type information, right? Like there's no. But in Dbus you do with a signature that, okay, this is not a normal integer that I'm about to serialize, so you can do something special. But in this case, it's not. So I will do something similar. I'll have to do something similar as Zbus, but it will not be the same, and it would be a bit. Yeah, we'll see. I'm going to look into it soon. Yeah. There's many people who have asked for file descriptors.
It's a question more about Zbus, where you have connections, right? If you have a huge code base and you need to reuse Zbus or use Zbus connection in different places, right? Is it preferable to create a short-lived connection every time, or create a pool of connections and reuse them?
In Zbus? Mm-hmm. No, you want to create one connection once and then just use that forever.
Okay,
yeah,
thank you.
That's all. Because you can clone it, like it's cheaply clonable, so you can just clone it as many times as you want. It's the same connection underneath.
Any more questions?
No.
Okay, as you exit the room, we'll uninstall Zbus from your computers, but we have a few minutes before the next speaker. So thank you.
Yeah, you're welcome.